Thank you very much. Thanks for the introduction, and thank you for the invitation, a chance to hang out here for a few days. That's for, speaking of telescopes in Chile, that's actually the SOAR telescope in Chile, which is not the telescope we use, but next to the one we use, and a condor in the foreground. It's always the coolest part of the astronomy job, is going to the observatories. I'll talk about direct imaging of extrasolar planets, as you probably know. And this is work representing, I'll be representing work by a huge team of people, both the people I collaborate with on studying extrasolar planets with current telescopes, most notably Quinn Konopecki, Travis Barman, and Christian Merois, and the large team that helped build the Gemini Planet Imager. Dave Palmer, who is our project manager at Lawrence Livermore, James Graham, who is our project scientist. I'd like to particularly highlight, since I'm here, Dmitry Savransky, who's a graduate student of Jeremy's and really one of the most brilliant postdocs I ever had, and was responsible for a lot of the bits of GPI that actually work, and is now off as a faculty member at Cornell. So outline, I'll talk about direct imaging in general. Since you have people here who do it, you're probably familiar with the key concepts related to it. This figure you can see, I like to show to introduce these talks. Of course, these are Galileo's sketches of the moons going around Jupiter. And it's sort of interesting as I kind of think of it as the first ever example of directly imaging not an exoplanet, but an exomoon. And what's interesting is, of course, Galileo was part of a movement to overthrow the geocentric model, together with people like Kepler, Tycho, Copernicus, and so on. Kepler produced a model that successfully predicts the position of planets. He took astrometry, he fit models to it, he could say where the planets would be over a course of time. That was compelling to scientists and sort of dethroned the geocentric model. Galileo actually made images, and that was sufficiently compelling to the public that got him locked up. And so in some ways, imaging exoplanets has a certain visceral excitement that you can't get from the little Doppler wobbles on a graph, at least in my biased opinion. But that's not the only reason we do it. Well, the real reason for doing it now is characterizing and understanding planets. And I'll start off with some pre-GPI examples of that, in particular talking about the HRD 799 planetary system and spectra of them obtained with the Keck telescope, some of the questions that are answered and some of the questions that are posed by those spectra. And then I'll talk about GPI, a little bit about the design, but not in enormous technical detail. I'll do a supplementary talk later in the week for Jeremy's group for anyone who wants to hear about super polished optics and aliasing errors and stuff like that. But our first slide, early science results, and the GPI exoplanet survey that we'll be carrying out with it. So when we talk about directly imaging exoplanets, it's important to say we're not looking at planets like Jupiter. We're not seeing reflected light from a planet. That's impossible with current technology. What we're seeing instead is the planet's self-luminosity, and it was recognized, and I think this is the first recognition of this. I didn't even read it at the time until somebody pointed it out to me, that when planets form, of course, a lot of gravitational potential energy is involved, and so they could potentially form extremely hot. They could have luminosities at ages of 10 million years, as high as 10 to the minus 5 for relatively massive planet-like objects, as opposed to the 10 to the minus 9 that, say, Jupiter settles down to at its current age and separation from the sun. And in turn, those luminosities could lead to high enough effective temperatures to be detectable, again, from the same paper by Adam and collaborators. These are, at the time, spectra of a variety of planetary masses compared to the sensitivity of the facilities people thought would be important at the time. Since he was at Arizona, he thought LBT would be important for these discoveries, and eventually it was. Maybe not quite on the time scale originally thought, as well as Nick Moss, Gemini, Certif, Sophia, etc. These models modeled the planets simply as black body emitters plus some reflected light. One of the next significant developments that has actually made this possible to see these planets with the instruments we have now is they're not black bodies. This was, of course, shown by the discovery of brown dwarfs, and again, fit by models by Adam. These are ensembles of models for planetary objects ranging from 100 to 1,000 Kelvin. And you'll notice none of these look like 1,000 Kelvin black bodies, which ought to be peaking sort of somewhere here. But they're particular wavelengths in the accessible part of the near infrared where they're very bright. And those are the wavelengths where there's no significant molecular opacity, so you're seeing deep, deep, deep into the interior of the planet where it's very hot. Where there is significant opacity, at wavelengths like this, you're seeing the cold tops of the planet's atmosphere. But there are some wavelengths where the near-infrared spectrum is really transparent. And so a planet with an effective temperature of 500 Kelvin, there are parts of its spectra where you're actually seeing to the 2,000 Kelvin interior or something even colder. And conveniently, those are the places where water and methane don't absorb. Water and methane are present in our atmosphere, so those are also the windows in which we can observe well from the ground. And so this non-blackbody nature makes these planets accessible not just to something like JWST, but to ground-based room temperature telescopes. Another complication that wasn't anticipated then but is becoming an issue now is the question of how planets form and how that influences their luminosity. And of course, there are a wide variety of mechanisms for planet formation. The classic sort of core accretion process, possibly modified by some migration as the planet moves in, that we think is how many large Doppler planets formed and how Jupiter formed in our solar system. Alternatively, there are processes that form planets through very fast global processes, through global instabilities, where a massive disk, as it orbits its star, if it's sufficiently massive and sufficiently cold, will begin to fragment and produce little condensations that could potentially become planet-like. Simulations that do this tend to involve relatively aggressive initial conditions to make it happen and form relatively massive planets, but it is certainly a pathway that could form planets. And the last picture of theoretical piece of the picture of theoretical predictions of planet properties was realizing that those initial conditions would modify these predictions about planet luminosity. The early models that I showed you the figure of from 1995 basically form planets like an idealized star kind of wafting down from infinity adiabatically and retaining almost all of its energy and entropy. That may not even be how stars form, let alone how planets form. If you form, on the other hand, a planet through a core accretion process, in these models by Mark Marley et al., it gives away a huge amount of its luminosity and a huge amount of its entropy early on. And so it's relatively, somewhere off here, it goes through a sort of accretion spike that doesn't even fit on the graph. And then it spends 10 or 100 million years kind of sitting at relatively low luminosities before it rejoins the cooling tracks that the other planets would have. And there's versions of this. This was sort of a binary model. There's versions of it by Adam and collaborators that have a knob where you adjust the entropy in a way that would be interesting if we had models of planet formation that could actually predict the entropy, which we don't. This actually would have been bad news for the searches for directly imaged exoplanets, in that if you believe most planets form through core accretion, the region we could reach with our first generation instruments at sort of about 10 to the 5th L sun wouldn't have had any planets in it. Fortunately, this paper did not come out before the tax gave us time to do these early direct imaging exoplanet searches, so we were able to look for it. And just to put these things in context now, here's everybody who gives exoplanet talks has to show a version of this figure. This is mine, or actually Eric Nielsen prepared for me, showing exoplanets detected by different techniques: RV, transit only, primarily Kepler detections, transit plus RV confirmation, Kepler and ground-based, microlensing, and direct imaging. And considered in this space, direct imaging is actually kind of pathetic. The total number of objects we've detected is very low compared to the assembly line techniques like transit and Doppler. And that's because we need these ideal conditions. We need very young stars. We need, with current technology, planets in relatively wide orbits for them to be detectable. So if this is all we're doing, we could be sort of embarrassed. But this figure shows in highlighted dots every planet that you could argue has been characterized, that we've ever seen any photon associated with its atmosphere. And even for extremely generous definitions of characterized, like signal to noise of 4 Spitzer secondary eclipse spectra in a single band. And in that space, direct imaging actually has done a pretty good job. Everything you direct image, you have by definition photons from. And 4 or 5 of these planets actually have quite high signal to noise, and in a couple of cases, quite high spectral resolution spectra, where you can see, I'll show this later on, individual molecules in their atmosphere. So although when we were motivating direct detection originally, we thought of it as a statistical technique, and it's still important as a way to probe planet populations at 10 AU that are inaccessible to other techniques. In my mind, the most important thing it can do now and into the future is characterize planets, is tell you something about their properties. And of course, the holy grail is future direct detection techniques that might be characterizing down here. But I'm not going to talk about that in this talk. There's now a whole gallery of directly imaged extrasolar planetary systems. I'll talk primarily here HRD 799, Beta Pictoris, which is lined up with a beautiful dust disk, Fomalhaut B, whatever it is, which is also lined up with a dust disk, Gliese 504, discovered by the SEEDS collaboration, HD 95806, Kappa NB, and a few more that are even younger than this that I'm not showing on this particular figure. So for most of this early part of the talk, though, I'm going to talk about HRD 799, system discovered by Christian Marois and collaborators in 2008 and 2010. It's a 30 million year old or so F0 star, 30 million years being why the planets are detectable, and of course why it was observed in the first place. There are 3 inner planets that have masses, assuming they live on those hot start tracks, of 5 to 7 Jupiter masses and effective temperatures around 1,000 Kelvin, and an outermost planet that has a mass of 3 to 5 Jupiter masses. in some ill-defined way, it's like a scaled-up version of our solar system. Of course, this is at much wider separations than any giant planets would have in our solar system. There's a whole bunch of other fascinating things about the system, including dust on various scales that I'm not going to go into for this talk. What I'm going to talk about is characterizing them. And to do that, it's useful to review brown dwarfs, because that was sort of the observational analog we thought of these planets. Brown dwarfs also shine because they're self-luminous. They have the same kind of chemistry in their atmosphere that planets ought to have. And so we thought we were looking for planets that would look like brown dwarfs. This is adapted from something by Adam Burgasser, adapted from somebody else. I actually don't think I could trace the history all the way back. But just to talk about how spectral types work. In stars, the very late stars, you see spectra that look like black bodies, primarily because you're seeing emission from condensed opaque clouds very high in their atmosphere. As you move into the warmer brown dwarfs, the type L dwarfs, that cloud layer moves down a little, and you start to see against that black body prominent absorption by carbon monoxide, among other species. Somewhere around temperatures of around 1200 Kelvin, a very abrupt transition takes place in brown dwarfs, and these clouds drop deep, deep, deep into their atmosphere. And as I was saying before, at some wavelengths where CH4 and CO don't absorb, you can still see all the way down to this opaque cloud, and so you see the sort of 2000, 3000 Kelvin type surface. But at other wavelengths where methane does absorb, you see the very, very top of the atmosphere, and that produces those very black body-like spectra, and produces very anomalous colors. Here's a color magnitude diagram in H minus K or J minus K versus absolute H magnitude, showing a range of brown dwarf-like objects. The L dwarfs, the warmer dwarfs, get redder, just like stars do as they get colder and less luminous. But suddenly it sort of abruptly zooms to the left as methane becomes important, and all the light at K-band gets sucked up by methane. And they have blue colors in J minus K and H minus K spaces. The surprise about the planets is that the directly imaged planets initially didn't do that. So a lot of people were out there looking for planets using the idea that they should have methane absorption. Whole instruments were built specifically for this very purpose. And it turned out that down to 1000 Kelvin temperatures, they don't have them, and they stay red. Alternatively, you could think of it that these planets having colors similar to the brown dwarfs are substantially less luminous. One way to account for that is to adjust. Instead of the really kind of ad hoc process where the clouds disappear in the LT dwarf brown dwarf transition, you can have a cloud knob that causes the cloud to gradually disappear, and you can produce spectra that roughly resemble the colors that we see. Here's a range of temperatures and ranges of cloudiness from some spectra by Travis Barman. Again, there's similar work by Adam and his collaborators. So with sufficient knobs, you can fit these colors successfully. Although when you do, there's still a problem in that the fits tend to produce relatively small radii for the objects. If you allow the radius to be an independent parameter in the fit, the radius comes in to be a small number, like 0.9 or 0.8 Jupiter radii. You can kind of even see that from the color magnitude diagram. These guys are at about 1 Jupiter radii. It's sitting well below it. It has the same color. Unless something really weird happens in the atmosphere, it's got to be smaller than a brown dwarf in physical radius. I'm glossing over a lot, so Adam is smiling slightly, but this is the simplified talk. And that's a surprise, because so far as we know, you can't actually make a massive object have a radius much below 1 Jupiter radii unless it's very old and very cold. The physics of the degenerate interiors cause pretty much every object, these are again the hot and cold starts, but once you get to old ages or even medium ages like 100 million years, the radius is pretty much independent of mass because they're degenerate objects just sort of sitting there as you pile more mass on them. At young radii, they can actually be bigger, especially if they're in the high entropy state, but it's really very hard to make a 20 million year old object have a radius of 0.9 Jupiter or 0.8 or 0.7. You could if you induced a very massive core into them, so it's possible that these objects are small because they have sort of hundreds of Earth masses of core in the center. I don't particularly like that explanation, but it's possible. Or it's possible that the atmospheres that are being pasted on them are giving us the wrong effective temperature and radii because we don't have all the physics of the atmospheres right. As an example, in a physics that is included, but there's still room to understand better, this is an image of Jupiter at 5 microns, IRTF image, just looking at the surface of Jupiter. If I had only this 5 micron data, this 5 micron photometry, and maybe a 5 micron spectrum to tell me something about the temperature, and I asked you what the radius of Jupiter is, when I say we measure radii, what we're really measuring is surface area. We're measuring the emitting area of the object. And so if you were 10 parsecs away from this and you measured the emitting area of Jupiter, you would get something that's sort of the size of the Earth, and you would say Jupiter is really tiny. It's not. What it happens is spatially, as well as in wavelength space, you're seeing the different places in the interior. People have put this kind of effect into their models, and it still doesn't fully resolve the problem, but it helps somewhat. And of course, they're only putting it in a relatively simple way, not a two-dimensional model of the planetary structure. So since we can see these planets and get photometry, not just photometry, we can get spectra of them. Low-resolution spectra confirm the sort of results from the photometry. They show carbon monoxide absorption. They don't show significant methane absorption. This is a spectrum HR8799b taken at Keck. They look kind of like an L-brown dwarf, a little bit pointier because of their low surface gravity, strong water vapor, not particularly surprising. That combination, that absence of methane and the presence of clouds, is explained using arguments about atmospheric circulation. To first order, if the planet's atmosphere is circulating, you can successfully push up carbon monoxide and maybe push the clouds up to higher altitude, and you can push down methane, which then in turn gets destroyed. The reactions between CO and methane run very slowly in the direction that makes methane, and so you don't need a lot of circulation or a lot of very fast circulation to successfully destroy almost all of the methane in these planets' atmospheres. So the picture, and these effects are seen in Jupiter and brown dwarfs, but they're stronger for whatever reason in the planets, is that a little bit of circulation is perturbing the chemistry away from the equilibrium, which should have made a lot of methane, in favor of a sort of CO-dominated atmosphere. It turns out not only can we get low-resolution spectra of these objects, but through clever image processing that I'm not going to talk about, we can get high spectral resolution spectra of these objects. This is a Keck OSIRIS spectra of R of about 5,000. People are allowed to ask questions, by the way. You can tell I talk very fast, but presumably you can try and slow me down, and I'll stop and interact with you. Let's see. So an observed spectra running along like this, and a model spectra indicated in yellow. The continuum actually turns out to be the hardest thing to recover. The speckle artifacts in the image can modify the continuum, can produce big blobs where 10 or 20 or 50 or 100 nanometers worth of spectrum is elevated or depressed. But the speckle... In this particular observation with Keck, we don't actually block out the star. These planets are bright enough, and the Keck AO system performance is low enough that we don't need a fancy coronagraph to do it. The Gemini Planet Imager that I'll show later, because it wants to look closer to the star, does have the fancy coronagraph. But we don't let the star fall on the spectrograph because it would fry the spectrograph, but we don't do elaborate Leo stops to control diffraction either.
So let's say that the planet is rotating. Is all the layers in the atmosphere rotating at the same speed, and will that change the spectral mechanism in alert?
This is the sort of question I would defer to Adam, actually, since he's sitting here. Yeah, almost certainly, it's not going to look like Jupiter, for example. Jupiter is heated from the outside as well as from the inside. Those bands are presumably related to that thermal structure. It's not unreasonable that it would be rotating at different speeds.
Could you maybe see that in the spectrum?
So there's one measurement. I didn't put the slides in, but there's a beautiful measurement by the VLT for the planet Beta Pic B, where they used an even higher resolution spectrograph than this, and they did resolve the rotational lines at, I think, 40 kilometers per second or so. We tried to do that. This spectrograph is R of about 4,000, and so it can't resolve the rotational lines at that level. We tried using Keck's equivalent of the RF 20,000 spectrograph, and for various technical reasons, we couldn't get enough light down the slit to do it. So there's one measurement of a rotation, and you certainly can't recover a line profile from it. You can just tell from cross-correlation that it is somewhat broadened. But it's not out of the question. It's an interesting thing as, for example, a project for an ELT or for an optimized instrument combining a really good coronagraph, a really good adaptive optics system, and high-res spectrographs. You might start to see something in line profiles, especially for these hotter planets. Because even though each individual line is detected at pretty tiny signal to noise, there's a zillion CO lines in there. There's a huge amount of information in the spectra. This is actually something people didn't initially realize. This is basically the same spectra as this one, and we took this spectra and thought, this planet is faint. We better bin the heck out of our spectra because it's low signal to noise. That's what you do when things are low signal to noise. And that was very stupid because there's a huge amount of information we are losing by binning because the noise, the thing that's making it low signal to noise, is not just random white noise. It's this highly correlated noise. So the continuum gets really mucked up, but the planet, the speckles in the star don't have CO in them, and so the individual lines are there. You can see the CO break. Most of the little wiggles you're seeing here are actually real CO features in the planet's atmosphere. So there's huge amounts of information coming out of these high-res spectra. I'll show you some cross-correlations. Yeah? The methane break is not significant in this spectra. The water isn't a break. Water is lines everywhere. So here's a good way to see the significance. This is the same spectra, high-pass filtered in the spectral direction to remove the continuum effects due to speckles, and then with just toy spectra for various constituents. So water, for example, lots of wiggly lines here, So that's what those are. So there's not a water band head, there's individual water lines. The CO break, CO is both a break, and that's obviously present in the spectra, but also individual features. There's one there that you can see if you're looking at it right with your naked eye. Methane should be doing this, including a break here, and you'll see that's not present. And of course, the simple way for somebody simple like me to see this is just to run cross correlations of those various templates with it. That's what's on the bottom. And you can see a cross correlation with CO shows a nice peak, and then some ringing because the CO lines are so uniformly spaced as we do the cross correlation. The water shows a beautiful peak. The cross correlation with the methane template is flat, so there's no methane present in this at our. These water lines are from the planet, yeah. When I say water, we mean 1,000 Kelvin steam, so you can separate them from telluric lines very cleanly, successfully. So it's not surprising that there's water on, it's hydrogen, oxygen. It'd be hard not to have water. It'd be impressive if we didn't. Although I'll show in a little bit, that does tell you something about carbon to oxygen ratios, for example, in the planet. So if we had a higher resolution spectrograph, the width of this would tell us something about the rotation velocity, and the position would tell us something about the three-dimensional motion of the planet. With OSIRIS, we can't do that, unfortunately. You really want is a sort of R of 20,000 integral field spectrograph to do this, and that instrument doesn't exist right now. But it's something really, again, obvious in hindsight, the idea that there's so much information in these lines that we were throwing away, and unfortunately, GPI throws away. More recently, this just came out in a paper by Travis Barman, Quinn Konopaki, myself, and Christian. HRD 799b, which is a little bit colder, does start to show the methane signature. You can see it most clearly in the cross correlation. There is a meaningful peak in the cross correlation, and model fits that include methane get a better chi-squared. Not very strong methane, but tiny little hints of methane. And because methane is such a strong absorber, you don't need a whole lot of it to make that be present in the atmosphere. I'm not actually sure I can say I see the methane break in the raw spectra. This feature, that one, I think you can say is there in the spectra, in the raw spectra, but it's clearly there in the cross correlations. With those spectra, something you can do is measure C to O ratios. It is model dependent, but it's not as model dependent as other parameters. It's hard for adjusting the cloud knob, for example, to screw up a recovered C to O ratio. You do need to know something about the effective temperature and gravity, so these models marginalize over a range of possible effective temperatures and gravities. But these are sort of delta chi-squared contours for either the entire spectra or the high-pass filtered spectra, and there are various arguments as to which one you should believe more. I think I believe the high-pass filtered one better, for the planet B and the planet C. And they converge to C to O ratios around 0.65 to 0.7, which is a little higher than solar. And so consistent with, like Jupiter, the idea that the planet's enhanced a little bit in solid material early in its life. Unfortunately, the star C to O ratio is very poorly constrained. The star is an F0 star, so it doesn't got all the lines to begin with, and it's an anomalous F0 star in various ways, with its atmosphere probably polluted by accretion from a dust disk. So I can't swear that this is different than the star at a statistically significant level. It is tantalizingly different than the star, which is what you'd expect for planets that sort of form through a core accretion process. Ruth Murray Clay and Oberg produced these sort of models where, depending on where a planet forms relative to the various frost lines, the gas will be enhanced in carbon compared to oxygen because all the oxygen freezes into water. In turn, if that gaseous material is what makes up the atmosphere of the planet will be enhanced in carbon compared to oxygen at the level that I say sort of tentatively would say we see. More objects, and especially planets around stars that we can get better, well, I was going to say better to C to O ratios, but we can't even agree on what the C to O ratio of the sun is, let alone. The planets are probably around 5 to 7 Jupiter masses. The best constraints, I'll show in a little bit, that depends on thinking you know something about the initial conditions, but there are also other constraints on the planet's mass from other techniques. Yeah, so I took those slides out because I wanted to get to GPI, but I can show you later on. The bad news is these planets, the outermost planet has a period probably of 800 years, so we see a tiny piece of the arc, but we can see it. And the fact that you can see, and they move like Kepler's laws. The one close is moving fast, the one further out is moving slowly. That's not a surprise, but the fact that you can see Kepler's laws from outside in another solar system is really one of the most amazing things I've seen in my life. The innermost planet has about a 40-year period, and so I'm trying to exercise better and eat well so that I can see it conclude an entire orbit. Or I decided to build an instrument that could see 5 AU planets so that I wouldn't have to worry about that. I'm deeply jealous, say, of Andrea Ghez, who has these beautiful galactic center stars that go around in 10 years. But so we can see them. Because we have only part of the orbits in 2D, we can't completely constrain their orbit. But because we can measure astrometry so precisely, you can fairly rapidly say something about eccentricities and inclinations of the system. In addition, and again, these are slides I didn't put in here, because they're 4 planets, they interact with each other gravitationally. And if they were extremely massive, if, say, I messed up completely and I lied to you, and these are brown dwarfs because the star is 1 billion years old, the system would not be stable. The 4 planets would gravitationally perturb each other. Dan Fabrici, among others, pointed this out almost immediately after the announcement of the discovery. And so in some ways, the strongest constraint on the masses of the planets comes from the orbits and from a stability argument. Actually wanted to show that in the context of this plot. These are the kind of luminosity and age ranges. And so they're inconsistent with these very cold planets, cold start core accretion, simple core accretion models. If they formed through a hot start process, they would have masses kind of 5 to 9 Jupiter masses. And the dynamical stability arguments actually say they can't be much more massive than that. If they were 10, no one's yet found a solution for even 10 Jupiter masses that can make the system stable on a long enough time scale for us to have actually discovered it. And so it's kind of a puzzle. In some ways, they look like a hot start global instability object, but it's hard for hot starts to make things quite that low mass. It's hard for hot starts to make the C to O ratio. I would say actually we don't have a good picture of how these objects formed at this time, but maybe we will in the future. Yeah, so the masses constrained by dynamics argue that the planets formed relatively hot, but the C to O ratio, and also the statistics of these planets. In general, those disk instability models like to make lots of huge 20 Jupiter mass objects that we don't find. So it's sort of a puzzle. Just an example of stronger methane absorption, and colder planets have just barely started to be discovered. This was discovered by the Subaru Seed Survey. It's a planet called Gliese 504. It's probably around the same mass as the 8799 planets, but substantially older. And so it's cooled down to 600 Kelvin or so and does show strong methane. This is an image in and out of a methane filter. Planet is there, planet is not there. So the methane absorption or the non-equilibrium chemistry does eventually go away, and strong methane does show up eventually, not in a way that's particularly well constrained. So I said, we've got a bunch of directly imaged planets. They're beautiful, very happy with them. But we'd like to say something, each of them now is still sort of a precious individual child that we study in great detail. We can't really say something about populations. I'd say somewhere between 20 million years and 200 million years methane absorption starts. It'd be nice to know when. It'd be nice to know why. It'd be nice to study a broader range. Some planets sit up on these hot start tracks. Are there any planets that sit down on the cold start tracks that were out of reach? To do that, we really need next generation instruments. Again, the sensitivity range we can get to right now, first, only lets us see hot star planets. And second, even for the hot star planets, only lets us see them to sort of 100 million years. And we've basically run out of 100-million-year-old stars in the solar neighborhood to look at in the northern and southern hemisphere. They've all been surveyed at with the state-of-the-art instruments, give or take. Somehow they keep finding 50-million-year-old stars no one had noticed before, but these days they're mostly M dwarfs that you can't lock AO systems on very well anyway. So if we want to find more, and if we want to, say, explore these initial conditions, we've got to get down to this kind of 10 to the minus 6 or below luminosity regime, and got to do it around a large population of stars to billion-year-old. In turn, doing that lets us look to sort of billion-year-old ages, getting a much larger population of target stars. We also want to look much closer. Here's our solar system for scale. Even the innermost planet in the 8799 system is kind of at Saturn scales. The existence of 5 Jupiter mass objects at Saturn and Neptune scales was sort of a surprise. That's what we're looking for, but it was a surprise. You'd like to know what's going on at 5 AU, but you can see in this image, there's this muck in here. That's residual starlight scattered by imperfections on the telescope mirror, scattered by turbulence in the atmosphere, and the diffraction that you were asking about, the stuff that a coronagraph would clean up, is stopping us from seeing planets closer in. And so that's the motivation to build an instrument that can actually do this. So that's the Gemini Planet Imager, a project that actually started in 2003 and got first light in 2013. It combines an advanced adaptive optics system, about a factor of 10 more powerful than the previous generation that Lawrence Livermore Labs built. It has a series of coronagraph masks, and I'll show a few slides about how they work to block the diffracted starlight. It has a precision infrared wavefront sensor JPL built to try and measure small perturbations in the wavefront at the science wavelength. This science instrument is not a camera, but an integral field spectrograph like the Charis one that's being built here, optimized for low spectral resolution, because that's what we thought was important back then, also because you run out of pixels, to make both, so for everything we look at, we don't get an image, but a spectrum. The Hertzberg Institute in Canada built the mechanical structure, and equally importantly, the software that connects all the pieces together. We spent a lot of money on individual mirrors, super polished so that we wouldn't scatter starlight off of them. All told, it was about $24 million, which is about the right price for a facility-grade instrument. with this capabilities on an 8-meter telescope. There's a European equivalent called Sphere that I won't show any slides from that's on the telescope on basically the same time scale. But I can't say what it costs because European accounting is too complicated for me. The adaptive optics system combines actually 2 deformable mirrors. I'll show a slide in a moment of the main one, but the main deformable mirror can't move far enough to fully correct atmospheric turbulence, and so you need a second deformable mirror, a coarse mirror we call a woofer that does kind of this to fix the broad atmospheric turbulence, and then a little mirror called a tweeter that fixes the fine high spatial frequency structure in it. Light is relayed between these super polished mirrors. Visible light is sent down into a wavefront sensor that runs at about a kilohertz, sampling atmospheric turbulence at a scale of about 18 centimeters mapped onto the primary mirror. The cost for that is that you can only observe stars brighter than about 10th magnitude. This isn't a general purpose instrument. It's designed specifically to look for things close to bright stars. What it means is we designed, so there's Gemini North and Gemini South. They're twin telescopes, right? They're not. So first, also, this is actually irritating me because it was just in the OIR study report. How big is the Gemini telescope? Yeah, it's not. So the primary mirror is 8.1, but the secondary mirror is massively undersized and is the pupil stop. So the Gemini telescope is a 7.9 meter telescope. The Gemini North telescope is a 7.9 meter telescope. The Gemini South telescope, the secondary mirror was mispolished, and there's literally a piece of cardboard around the edge of it blocking the downturned edge of the mirror that stops Gemini South down to 7.8 meters. So what it means is we would have 44.0 actuators across Gemini North. In the case of Gemini South, we have this 43.2. That means there's a little bit of the primary mirror that sort of sticks out beyond the sampling of the wavefront sensor, which only runs 43 subapertures. So we're on the 7.77 meter. In spite of all that, we actually got the size of the secondary obscuration wrong, and I can tell you about that at lunch or something like that. Gemini South, which is where we deployed, is a warm 8,000-foot site. So we operate around 5 Celsius most of the time. So we're not cooled. So we're limited to... The spectrograph is cooled. So the spectrograph is cooled to 80 Kelvin. It's a cryogenic Mercator-based spectrograph. I'll show some slides about it. But the main body of the AO system is warm. And that does limit us to wavelengths of 2.5 microns or shorter. Again, that would be an interesting capability that the adaptive secondary instruments like LBT have, is to go to longer wavelengths, which is a very nice complement. Something we didn't fully appreciate then is just how red the planets turn out to be. And in practice, LBT is almost as sensitive as we are, even without a fancy AO system, because they can access those 5-micron wavelengths. The reference object is always the star. So we're not using a laser guide star, if that's the question you're asking. We don't use a laser. We use the star. So I worked at Lawrence Livermore. I spent a lot of my life trying to make these sodium lasers work. And if God had wanted me to use a sodium laser, he wouldn't have made all those 8th magnitude stars for us to look for planets around. So, because we want to look at nearby stars, we can use the star itself. And in fact, we probably couldn't build a laser. Well, Livermore could, but nobody else could build a laser bright enough to lock GPI onto successfully. So those indicate the deformable mirrors in the system. So those are the mirrors that correct for atmospheric turbulence. I apologize for not giving more background. So 1,000 times a second, those mirrors are changing their shape. This one is a piece of glass with piezoelectric actuators glued behind it. It's about this big. Each actuator is spaced about 5 millimeters apart. This one, the really wavy one, is a piece of silicon. It's a MEMS, a microelectromechanical device that's micro-machined like a microchip with 4,000 individual actuators. You can't even see them in this figure in a space the size of a quarter. And that's what lets GPI be small enough to fit on the back of the Gemini South telescope. Here's the wavefront sensor that measures the atmospheric turbulence. It's a Shack-Hartmann wavefront sensor, 43 subapertures across. This is, I think, telescope simulator data, but you can see the details of the telescope structure. You can also see defects. The MEMS mirror did have 3 defective actuators in it that we have to mask out later in the system. There's the mechanical system being put together in a clean room. The coronagraph you're asking about, ours is actually a modification of Leo's classic coronagraph, something Reme Soumet, who's now at Space Telescope, was responsible for, but it was built at American Museum of Natural History. It takes the entrance aperture of the telescope and it apodizes it. It smooths it in a grayscale fashion. It's somewhat similar to the shaped pupils that the group at Princeton devises, except that it doesn't, which is also an apodization, just a binary apodization, except that it doesn't do all the coronagraph work just with the apodization. That's very hard. To completely block diffraction, you'd have to have the transmission drop to 0 very smoothly, or use these complicated patterns that Jeremy's group is excellent at deriving. It combines this apodization with Leo's coronagraph, which is a focal plane stop to block the core of the star, and a Leo mask. And these apodization functions are designed by Remy in a way that sort of makes them eigenfunctions of the whole system, such that all the residual light that makes it past this focal plane stop diffracts out of the beam and is blocked in turn by the Leo stop. And there are complicated papers on. You can read. In this, the physical size of it. Oh, I mean, let's see. This is the pupil plane, so we taper the transmission of the telescope. Yeah, so we put this donut on. The suppression of diffraction is down to about the 10 to the minus 7 level, which is the right design level for a ground-based instrument, very nicely. To manufacture these grayscales, they're kind of metal on glass microdot patterns. Here's a zoom in of these. Individual dots are sort of, in the first versions, they were 2 microns. It turns out when you try to put 1.5 micron light through a metal on glass 2 micron dot pattern, interesting physics happens. And it's the kind of interesting physics people win Nobel Prizes for, so we're not smart enough to understand that. So we made the halftone pattern bigger at about 10 microns, and then we calibrated these experimentally, excuse me. So if the metal pattern covers 90% of the glass, you do not get 10% transmission. The transmission is enhanced by surface states in the metal. And so we took all these masks to Brookhaven, calibrated them, adjusted the grayscale to do it. You also see this grid pattern. I'll show you what that's for in a few slides. So the apodizers live here in the instrument. The focal plane, the blocking of the star, is actually done backwards. We focus the star on a mirror with a hole in it, so the star falls down the hole and is then available for wavefront sensing and stuff like that. The planet bounces off the edge of the mirror. There's the hole. And then finally, the Leo stop lives deep inside the infrared spectrograph and also includes a little bit of stuff to block the defective actuators. The infrared spectrograph you were asking about at 80 Kelvin, it was built by UCLA, by James Larkin's group. Here's a picture of it. It's extremely red. It was painted by a company that mostly does sports cars, because that's what you get in Los Angeles. I think the technical term is midlife crisis red. It's cooled by some exotic cryocoolers, and in the Jeremy's lab version of it, I'll talk about the cryocoolers at some length if people care about it. It's a lenslet integral field spectrograph, so it focuses the beam from the telescope onto a grid of lenslets in a focal plane, and then slices that focal plane up with the lenslets, disperses it with a prism, and so the output in the end is an array of little microspectra. At every piece in the field of view, here's an image of lab test data. If I zoom in, at every piece in the field of view, there's tiny little microspectra corresponding to 1 pixel. A data pipeline written initially by René Doyon, Jerome Maire, but really taken over by Marshall Perrin at Space Telescope, who is amazing, picks those up and in real time reconstructs them into 3-dimensional data cubes. I'll show examples of that when I get to real data. We integrated the whole thing at UC Santa Cruz in a clean room to keep it relatively dust-free. There's the spectrograph going in. We did flexure testing. Gemini is a Cassegrain telescope, so it has to go all over the sky. We did temperature testing. It has to operate at -5°C, so we built a meat locker around it, chilled it down to -5°C. We calibrated their open-loop flexure compensation models that read temperature sensors or read the telescope orientation and realign it. It mostly stays aligned, independent of telescope orientation. After about 3 years of integration and testing, we put it in boxes. My small child helped us with the process of loading it from the boxes onto a truck. You don't drive all the way to Chile, you can't. So we drove it to Los Angeles, airplane to Lima, airplane to Santiago, truck up to the top of Cerro Pachon. I did not travel with the instrument because I don't speak Spanish, and also it would have been a little too scary to watch 10 years of my life be trucked around twisty mountain roads in Chile, but it made its way up there successfully. Actually sat down in the basement of Gemini for a month and a half because we were there before they were ready for it, but then unpacked it in their clean room. I did finally fly down and was reunited with it. Happy to see that it survived. Mounted it on the back of the telescope. Here's the back of the Gemini telescope structure. Gemini actually mounts up to 5 instruments at once, which is very convenient. We can be here looking straight up, but other instruments, like their classical optical spectrograph, can be off to the side. And so that lets them switch between instruments, which is very nice when you're commissioning or when conditions vary. It's one of the things Gemini actually does right. At H-band, 1.65 microns, the sky is a pretty negligible source of background. At K-band, sky or thermal background, more precisely, because the instrument is warm, is significant. It's not a major issue when you're looking for point sources like planets. It is a major issue for recovering emission from dust. And I would say we probably subtract it down to kind of I want to say 16 or 17 magnitudes per square arc second or so. Flat fielding is complicated for these lens-lit integral field spectrographs. So we've experimented with a variety of approaches to flat fielding. We have a laboratory flat of the detector itself. Again, this could be done in detail in an offline discussion. We generate dome flats. They turn out not to help that much. The detector is flat enough and the spectra averages over enough pixels that at the level we're operating, which is kind of 95% accuracy photometry, the flat field doesn't make a significant difference. Yeah, I may not show the slide, but we did experiments, for example, where we looked at a white dwarf companion to a main sequence star because we know the spectra and the magnitude, and so we recover the white dwarf spectra basically to 5% errors with or without flat fielding. Scattered light, so we built the thing in a clean room. Although there's a hair on one of our focal plane masks, I don't know whose, but it's there. We super polished every optic. So we found a company in Fremont that could, every off-axis parabola in the instrument is polished to about half a nanometer RMS wavefront error. So there's no significant contribution to scattered light from Fresnel effects or so on. We inject artificial sources and we can check the residual contrast from them. So the main sources of scattered light are wavefront error type effects, imperfections in our wavefront sensor sending the deformable mirror to the wrong shape, for example. But the instrument itself doesn't scatter light at any significant level, except for that one hair on the focal plane mask. So we actually, there's some papers I can refer you to by Christian Marois. He did a very elaborate Fresnel optics model where we put dust on different surfaces in the instrument, saw what the effects would be, used that to set our clean room requirement. It was a pretty good clean room, although we found a lizard in it once. But that's what happens. Santa Cruz is an odd place to integrate instruments. But technically, there was only one lizard, so per cubic foot, it does not violate the class 1000 standard. So I guess. It wasn't on the instrument either. So. And it didn't make it to Chile as far as I know, which could be an environmental problem. So we did a lot of modeling, and I can discuss separately this on scattered light all through the instrument, and it basically, I think, did achieve it. So first light, it basically worked out of the box, which made Gemini very happy. There's the first light team down there from late 2013. There's a first light image. I'll show a lot of GPI images, and so it's worth talking about what you see in a GPI image. The star is hidden, is falling down this hole, but the hole doesn't look black. Of course, Arago/Poisson have these arguments about it, so there's residual diffraction that fills in what should have been a dark hole. And in the case of our chronograph, it actually takes the form of a ring, although you'll see it varying with wavelength. These 4 dots here are copies of the star produced by that grid that I showed you on the appetizer. So the thing you want to measure is how faint a planet is compared to the star, how far away it is compared to the star. The star has fallen behind this mask, so you don't know where the star is. So we induce, with this diffraction mask, 4 copies of the star whose position we know and whose photometry we know, although they're not the same brightness. All the physics I can think of says they should be the same brightness. They're not. But in these white dwarf experiments, we calibrate the relative brightness well enough to recover the position. Harder to see in this light, there's a sort of cross pattern that's purely horizontal and vertical. And that's residual aliasing in the wavefront sensor as it measures the high frequency components of atmospheric turbulence. And we have a thing that's supposed to clean that up that doesn't clean it up perfectly. Spheres appears to work better, and I can't honestly say why. Oh, yeah, sorry, I apologize for that. This is 2.8 by 2.8 arc seconds. So one of the trade-offs of having this instrument is it's a postage stamp. It's only going to look close to the star. So residual aliasing there. You can see there's little bumps here. This is the sort of up-down pattern on the deformable mirror. It's the highest frequency you can actually make with your DM. It's called waffle mode. I think you can see from where you're sitting a sort of butterfly or hourglass shape pattern. That's the dominant source of wavefront error in the instrument when we're locked on atmospheric turbulence, and that's due to time lags. We measure the wavefront every millisecond. It takes about another millisecond to do the calculations to set the deformable mirror, and so we're always a millisecond and a half behind. That's inescapable in any control system, although it's longer than in hindsight we would want it to be. The winds at Sarah-Pachon are faster than the models we have, and so that really dominates the atmospheric turbulence. In this particular case, the wind is blowing in this direction. That scatters light preferentially in those directions. And we do see a very big difference in final sensitivity between nights when the jet stream moves over the mountain, which are just disasters, and nights when the jet stream is not over top of the mountain. We have some algorithms that were developed at Livermore that could predict that atmospheric turbulence a millisecond or so into the future. They're somewhat computationally intensive, but they're being tested right now on other AO systems, and if they work, we might retrofit them onto GPI. Or we could potentially find a faster CCD or faster computer to speed up. There is what you can see, what's called a dark hole region. In our case, it's square, but it's fairly weakly defined because the aliasing fills it in to some extent. Also, I think because we're not kicking up a lot of extra high spatial frequency errors, a good way to make a dark hole is to put a lot of high frequency errors on your DM, and then the edges of the field get bright, makes beautiful pictures, but it's not really what you want to see. So here's some raw integral field spectrograph data. I can zoom in again, and then I can activate the data pipeline to reconstruct it. That's a GPIO image of Neptune. So every time we take data, this is what we get. We get a three-dimensional cube stepping from different wavelengths, in this case in H-band, across the whole 3 arcsecond field of view. Neptune, it's not like we don't know what Neptune looks like, but you can see structure in its atmosphere in really 3 dimensions. You can see clouds that stay bright for a long time or up at relatively high altitudes, so they don't get absorbed by methane as much. Clouds that go away are deep in the atmosphere, and they go away as you go into the methane bands. And the equivalent on planets is the sort of thing that exoplanets, the sort of thing that we're ultimately looking for. So here's, for first light, of course, we concentrated on known planets. Here's Beta Pictoris, a famous exoplanet system. Anybody sitting in the back, can you see the planet? A lump there. Yeah, so even in the raw data, before I've run it through the data pipeline, you can actually see the Beta Pic planet if you blur your eyes, if you turn the lights down, et cetera. But it'd be a lot easier if I reconstruct the cube. So here's a single wavelength slice, so just one wavelength, I can't remember what wavelength, out of the data cube. The only process, so when you see these, all the images I showed of HRD789, a heck of a lot of processing happened in them, elaborate principal components analysis to remove the scattered starlight. That did not happen here. This image has had a very simple high-pass filter to get rid of the butterfly, nothing else. And you can see the planet, and you can see the 4 reference without doing all these fancy PCA-type games. For comparison, there's an image with the fancy PCA processing from the Gemini Niki instrument, the best thing Gemini had before GPI got down there. You can see the planet, not quite as well as our image, with, of course, the key difference being that that was 3,952 seconds, and that was 60 seconds with GPI. So it's actually doing what it's supposed to. So we were happy. Here's of course, we can still do the fancy processing. These are time and wavelength series. On the right, you can see scaling through wavelengths. The diffraction artifact's position changes with wavelength. The speckle artifact's position changes with wavelength. Fancy processing can remove that. The same thing through time. As you track a star across the sky, parallactic rotation causes the planet to move relative to the star. The artifacts stay the same. It's interesting to note these are extremely close to identical. GPI, one of the things we worked very hard on was to make the instrument very achromatic, so the PSF is essentially the same at all wavelengths. These are not as much the same, and that's because atmospheric turbulence is fluctuating. That's not something we have control over in complicated ways. So we do very well with the multi-wavelength processing. In turn, that will be very powerful for detecting planets if they have strong methane features, and the hope is that we'll reach the regime where we can see planets with strong methane features. So there's the stacked and combined set. Beta Pic B, as I mentioned, had a disk. Here's a VLT image showing that the planet orbits in the plane of the disk. With our data, our astrometry is high enough, and Beta Pic has a short enough planet, we can do orbit fitting versus time, X and Y offset, discovery images from the VLT a long time ago, GPI image, a bunch of other images in between. You can constrain the orbit pretty well, especially over moderate to short time scales. James Graham, in our collaboration, ran MC orbit fits, getting a semi-major axis of about 9 AU, inclination of 90.7 plus or minus 0.7, and that minus 0.7 is important. We'll see in a second. Eccentricity very close to circular, not wholly surprising because it's sitting in the middle of a disk. The minus 0.7 does mean there's a chance that the inclination of the system is exactly 90.0 degrees. So there are a family of orbits that are consistent with passing through zero separation around 2017 or so. Right now, that's not well constrained. Only about 5% of the orbit family does that. There is historical evidence. There's actually a 1981 measurement that shows a hint of a transit around Beta Pic. It probably isn't a planet. It's probably lumps in the debris disk doing the transit. But it would be really amazing. If we could actually get a transit of a directly imaged planet, then theorists would have nowhere to hide. They would have to get the radius exactly right in their models, or we would laugh at them. But 5% chance, the error bar range for the transit is probably on the order of 3 weeks. So figuring out how we're going to hunt for the transit, it's worth doing, is an interesting, complicated question. We looked at HRID 799. Let me just pay attention to time here.
What's the date relative to expected JWST launch?
The transit dates are pre-JWST launch, unfortunately. I think what we really wanted, it'll be a deep transit. So we should be able to get a radius out of optical photometry from the ground. So really what we need to do is arrange some kind of ground-based network. And I think the transit duration is on the order of 14 hours. So with enough ground-based telescopes doing monitoring, it's possible to do this. Or a little, this is actually a good CubeSat project, and people have talked about transit CubeSats. or most, but I think most can't observe beta pic. I can't remember the exact reason, but it can't. As of course we're continuing to refine the orbit, so we should be able to say much more accurately whether it's going to happen or not happen as we get closer. But there'll still be a couple of weeks of uncertainty in the date because, of course, as it gets close to transit, it goes in the hole, and we can't measure its orbit anymore, frustratingly. HRD 799 comparison between 60 minutes Keck, 24 minutes of GPI. You can see the orbits. You can see that this planet has moved significantly compared to the Keck data from 2010, GPI data from 2013. We can recover spectra like the Keck spectra, except that instead of taking 5 or 6 hours, it takes about 30 minutes to get the low-res spectra. These are model fits. Trying to decide how much detail to go through in the model fitting. It's worth saying a little bit about it just to highlight uncertainties in modeling that are still going on. So observations here. Yellow data is Palomar spectra, probably lower signal to noise than the error bars indicate. The points with the error bars here are photometric observations, mostly mid-infrared by the LBT, which are extremely important in constraining the planet's property. And then this is the G5 spectra, in this case, a K-band spectra covering it. The black is a model fit by Didier Saumon and Mark Marley, in which they forced the model fit to have the radius that they think a planet should have, based on our understanding of the interior of a planet, the equations of state. And as I said earlier, the problem with that is those radii are large. The effective temperature comes out relatively low. The radius comes out relatively large. That black line, which sort of fits everything, you can see does a really terrible job. In particular, it really messes up the luminosity of it massively overpredicts the luminosity of the object compared to 5 micron observations that have been taken at Keck and other places. Doesn't do too great at 3 to 5 microns either. Interestingly, if you fit just the GPI spectra, which is, I think the line is blue, but I'm colorblind, so somebody who's not colorblind should tell me what color this line here is. Pink or blue? Pink? OK. So the pink line is a fit just to the GPI spectra, so it's just fitting these points in here. And you actually see it does a really surprisingly good job, especially in HRD 799C, of hitting, and D as well, of hitting the photometric data points. So if you fit only the spectra, you can actually successfully predict the photometry, saying that spectra is good enough to constrain the properties of the objects, with the caveat that that fit still has the usual problem of getting the radius too small. If you really believe the radius is 8 or 9 Jupiter radii, you need sort of 1,000 Earth mass cores. That can't be what's going on. There's got to be more physics in the atmosphere than we know about. I mentioned it earlier. Beta Pic, we also have a spectrum of. Beta Pic is substantially hotter, and so it looks more like a young field L dwarf. There's fewer anomalies in its spectra. The last couple of science bits I want to talk about are polarimetry. So in addition to spectra, we can switch GPI into being a polarimeter. Prisms move in, prisms move out. Don't get spectra anymore. You get polarization of everything you look at in the field of view. And here's an example. This is a recovered Stokes cube for Titan. So total intensity, Titan looks like Titan. In polarized light, Titan's limb is highly polarized by double scattering. Light goes in, hits something deep in the atmosphere, makes a right turn, comes up to the surface, makes another right turn, and comes back to you. And so you get these polarization vectors pointing into the center very clearly. Again, not something that you can't measure in other ways, but a nice example. What the polarization was made for, of course, was looking at dust disks around stars. And so here's a time series of the dust ring HR 4796, one of the most famous bright debris rings. You can see the field rotation causing it to move with respect to the scattered light. You can see a really beautiful detection at H-band in this case. If I add all those images up, the ring is very nicely detected in total intensity. If I look at only polarized light from our polarization mode, that's what you see. So all the scattered starlight, of course, is unpolarized. The ring is extremely polarized, but not at all in the way we thought it was going to be. It's extremely polarized on one side and not at all polarized on the other side. What we expected, if you scatter off small grains, is that the intensity should have been that way. Forward scattering is much more efficient. So the total intensity should be much, much brighter here than on this side. Those small grains polarize basically symmetrically, and so the fractional polarization should have been the same on both sides. And in fact, it was the opposite, so we checked if the pipeline was wrong, but nope. It's doing. This is H-band, 1.65 microns, although we have K-band data too. I can recover the total intensity through fancy PSF subtraction and the polarized intensity. This is, when I say I, actually, let me be precise. This is Marshall Perrin, primarily at Space Telescope, together with Gaspard Duchesne, who did most of this model fitting, and of course, James Graham, who's kind of our polarization guru. I can recover the fractional polarization, not so well close to the star, because I can't get the total intensity close to the star. I can get the polarized light, but not the total intensity, so I can't get the fraction. And then you can compare that to models. And you see, as you clock your way around the disk, the polarization peaking at particular scattering angles and dropping to relatively low, extremely low levels on the backside of the disk. That's not what you would expect from Mie scattering. Here's a simple Mie scattering model, and you can see the fractional polarization is highest at the edges, but symmetric on both sides. This is basically the opposite of that. You can kind of make that with larger grains. Here's a series of models, fractional polarization versus angle, for fluffy large grains of various sizes. But it's hard with that to get around the problem in total intensity. Those grains are still much better forward scatterers than back scatterers. And so the ring still should be much brighter on one side than another in total intensity, which it's not. And so the model Gaspard and Marshall came up with was that the ring's potentially optically thick. Not extremely optically thick, but tau about 3 to 5 or so with large grains. And so in one direction, we're seeing backscattering off the outer surface of the ring. Doesn't polarize very well when you backscatter off big grains, but the intensity is good. In another direction, we're seeing forward scattering, but because the ring is about tau of 2 or 3, some of that forward scattering gets absorbed on its way to us. That model's a bit just so to make it do that. In turn, it would imply that this ring is dynamically very, very cold. We know the total mass of dust in the ring. I can't remember what thickness it translates to, but it would have to be, it's not quite Saturn's rings, but it's kind of like that. It would have to be orbiting in a very, very narrow plane, which would be interesting. People always want to attribute these rings to an invisible planet that's causing the ring to exist. I don't know. We see a lot of rings, we never see the planet, but it would, I think, be hard to make it quite so dynamically cold with a high-mass planet anyway. Contrast, we're operating at about the 10 to the 6 level in contrast. The goal was to be down at a few times 10 to the minus 7. We're building up models to understand why we're not getting to full performance. Now, the goal was to be sort of 100 times better than anybody was doing at the time, and that's what we wrote down in 2003. The problem is, since 2003, we've gotten a lot better at using the existing AO systems. They're sort of a factor of 10 better than they were, just in terms of this very fancy image processing. So combined with that, GPI is now sort of only a factor of 10 better than conventional imaging, which is still good. This is a nice paper. There are groups other than us using it. This is a very young disk, B4046 Sagittarius AB. It's actually a binary. In polarized light, you can see this beautiful multiple ring structure. It actually fills in very nicely SMA observations. So there's a SMA observations show in millimeter a large cavity. GPI shows actually a lot of light scattering out of that cavity. And so that implies that the larger millimeter scale grains are segregated compared to the small dust grains, which is something you could expect to be happening in planet formation. Lots of GPI images. Just in my last minute or two, I guess I'll talk about the survey that we're going to carry out. So Gemini has allocated us 900 hours of telescope time to do a very systematic large-scale survey. It's a very sensible decision on their part. They didn't say, because you build the instrument, you get to do the survey. They had a separate competition for a survey team, but we proposed and won. And so we're going to observe approximately 600 young stars, ranging from young association stars with sort of ages under 100 million years, adolescent stars that are closer but older that have been identified through a large spectroscopic survey looking for age indicators in stellar atmospheres, young A stars because A stars seem to have planets more often, some SCO-SEN stars that honestly I'm not sure why are on the target list, but let me make every decision, a handful of stars with debris disks, although we're trying not to preferentially target the debris disk stars. People say things like, image exoplanets are often correlated with debris disks, therefore debris disks must be related to exoplanets. But we observed stars like 8799 in the first place because it had a debris disk, and we sort of thought this might be true. So we're trying to avoid that fallacy here and just look at every young star we can find so we can answer these questions relatively rigorously. Simulations, these are ones by Dimitri, say that depending on what the universe provides us, this Marley versus Burroughs actually is really cold start versus hot start because that's the way Dimitri classified things. In a cold start universe, we would find sort of 10 to 20 planets. In a hot start universe, we might find as many as 40 planets. These simulations were probably very optimistic, so I don't think we're going to find 40 planets. You mentioned fitting orbits. This is an example from 8799 just to show with partial orbital arcs you can fit orbits. Never exactly, but you can constrain ranges of possible eccentricities. For a GPI survey, here's a simulation of the limits on eccentricity versus how often we observe a given star, even over a 3-year time. And for some planets, you can rapidly constrain the eccentricity to be, say, below 40%, or rapidly constrain it to be above 40%, depending on the eccentricities you put in. And even though we'll never measure a single eccentricity at high accuracy, over a population of stars, we can meaningfully distinguish between a universe in which, say, all the 10 AU planets go around in circles, like they do around our solar system, or in which all the 10 AU planets are on crazy eccentric orbits, like the high-mass Doppler planets tend to be. So statistically speaking, it's probably one of the strongest diagnostics of planet formation processes. We've started to have candidates. We've imitating the Kepler people, we're numbering them as GOI, GPI, object of interest. We're not going to have 1,000 of them, so we're not going to need more than two-digit numbers for this. So one of the things that happens in this game is when you find an object close to a bright star behind the mask object, of course, you don't know if it's a planet, or in this case, a brown dwarf, or a background object. And so traditionally, you go back and reobserve it about a year later to see if it shows common proper motion, indicating that it's real, or non-common proper motion, indicating it's a background object. In this case, this one would have been about a 20 Jupiter mass brown dwarf. The total number of background objects I expected in all the stars we had surveyed at the time we did this observation was 0.01 background objects out of the 50 or so stars that we'd observed as of the end of last year. The good thing about GPI is rather than having this lingering hope, you can get your disappointment almost immediately because we recover a spectra of every object we look at. And so literally while I was on the airplane back from Chile, my postdoc, Eric Nielsen, analyzed the spectra, fit it to models, and said it's a K-star. So even though there's supposed to be only 0.01 K-stars in the survey, we got one within the first 2 months. And then we actually did the astrometry to confirm that it was right, but we didn't really need to. So it's actually an interesting paradigm shift. This sort of happened with transits. In the old days, nobody believed a transit unless you had a Doppler measurement to go with it. But ultimately, Kepler has enough statistics that you don't need to do that anymore, in part because we have now priors on the number of planets. We have priors on the number of background objects. You can make that distinction with Kepler, and I think we can start to make that distinction with imaging as well. That when you have a spectra, if it shows sufficiently distinct features, you can argue that it really is a planet without having to wait the whole year to get the proper motion. And so if I get to come back sort of 2017, a characterized exoplanets figure might look like this, although of course I've pretended that Kepler stops observing, so there'll really be a whole bunch more here. But GPI should fill in a significant piece of this distribution, including potentially planets on a couple of AU scales or on Jupiter mass scales around a significant population of stars. So we've had about 10 papers with GPI, not just by our group, by a large number of people using it as a facility instrument. Campaign operations have started. We've looked at about 88 stars, seen the occasional Chilean fox. And over the next 3 years, we should get about 600 stars. So I will stop there.